So welcome back to all determinants all the time. In the previous section, we looked at the basic idea of how to compute a determinant using something called cofactor expansion. Cofactor expansion is nice if there's a lot of zeros in a particular row or a particular column, but if you've got a completely non-zero matrix, it's pretty painful even for a 4x4, not to mention a 10 by 10 or a more realistic real-life example of maybe 1,000 by 1,000. So it's time for us to get smart about determinants. I wanted to start by looking at a couple examples from your homework on the previous section. So these are 21 through 24 from section 3.1. And you should have already done 21 and 23, but just to recap, they were asking you to explore what changes about the determinant when you do row operations. So for instance, in 21, they were giving you a little 2 by 2, 3, 4, 5, 6, and asking you to compare the determinant of that one to the determinant of one where they did a row operation. And they didn't even give you a specific row operation, they made it generic. So they multiplied the first row by k and added it to the second row, and that became the new second row. You would think that would change the determinant, but let's take a look. So the original 2 by 2 matrix here, we know the determinant formula for a 2 by 2 is just AD minus BC. So the determinant here is 3 times 6 minus 5 times 4. So 18 minus 20. So the determinant is negative 2. On the other hand, for this one where they did the row operation, you'd think the determinant would change by k or maybe by 3k or something, but let's take a look. So now the determinant for 2 by 2 is still 3 times 6 plus 4k minus 5 plus 3k times 4. And we have to do a little distribution here, but that's 18 plus 12k minus, that would be 20 plus 12k, and it's still parentheses, so minus 20 plus 12k, and you notice the 12k and the minus 12k go away, and you've still got 18 minus 20, and you've still got minus 2. Shocker. But this is not an accident. There's nothing special about 3, 4, 5, 6, or about a 2 by 2 matrix. It is always true for all matrices everywhere that if you multiply one row by a scalar and add it to another row, the determinant doesn't change at all, which is a beautiful thing. I'm not going to go through 22, but they did row operation the other direction. Same thing happens there. You get the 3k times 4, and you get the 4k times 3, and those cancel each other out. Okay, so let's look at 23. 23 is a 3 by 3, and first one's just a basic 3 by 3. So next one, they've multiplied the top row by k. So they're going through the 3 basic row operations, right? You can add a constant multiple of one row to another row, you can multiply a row by a constant, or you can swap 2 rows. So in 23, first time around, let's do the cofactor expansion, and I am just going to expand across the top row. Don't forget our plus, minus, plus there. So the determinant will be 1 times 16 minus 12. 16 minus 12 is 4. 1 times 4 minus 1 times negative 6 minus negative 8, so 2. And then plus 1 times 9 minus 16, so negative 7. So that ends up being what? 4 minus 2 is 2, minus 7 is negative 5. So notice what happens on the second one. I'm going to expand across the top row again. And notice all that really changes is instead of 1, 1, 1, I've got k, k, k. No reference to any hate groups from the civil rights era. But the important part here is that the cofactors are still the same. So the determinant this time is going to be k, and then this is still 16 minus 12. So it's still k times 4, and this will be minus k times 2, and this will be plus k times negative 7. I can factor the k out of all of this and add the rest of it together. So for 23, we sort of discover that multiplying a row by a constant multiplies the determinant by that constant. So that's easy enough. And then for the last one, where they have swapped two rows, they had ABC in the first row and 3, 2, 2 in the second, and then they swapped it on 24. I'm maybe not even going to do the whole determinant here, although it wouldn't be hard. But imagine expanding across the first row here. You get the determinant is A times something minus B times something else plus C times something else, because you have the checkerboard pattern of plus, minus, plus. For the second one, I'm going to choose to expand across this row. And keep in mind the checkerboard pattern, right? It always starts in the top left corner, so that 3 is a plus. That'll be a minus, plus, and a minus. So now the determinant here is going to be negative A times, and I'm crossing out that row and that column, same cofactor. It's still going to be 3 times 6, or sorry, I'm crossing out the first one. It'll still be 2 times 6, so 12 minus 10. And when I cross out A here, it's still going to be 12 times 10. So same cofactors, but just all the signs are opposite. So whatever this comes out to be, something, this is going to be negative something, or opposite of it. If this one was negative, this one will be positive. So swapping two rows changes the sign of the determinant. And there we've just explored all three row operations. So this is Theorem 3 out of 3.2. It says suppose you've got a square matrix. First of all, if you add a multiple of one row to another row, the determinant doesn't change. And you feel like that's probably like 90% of what we do with row operations, is add a multiple of one row to another row. Doesn't change the determinant. If two rows are interchanged, then the determinant changes sign. And finally, if you do happen to multiply one row by a k, then the determinant multiplies by k as well. It turns out, it's pretty nice that in doing row operations, to get down to row echelon form, you never have to do that one. You only have to do the first two. If you want to get to reduced row echelon form where there's ones on the diagonal, that's when you end up multiplying by 1/3 or by 2 or something to get those ones. But if you don't care what numbers are on the diagonal, if you just want zeros below, you only need A and B. And A doesn't do anything to the determinant. B only changes the sign. So we sort of get this way of finding a determinant. And there's a little bit of notation here. So it says the determinant will be the product of the pivots. Because keep in mind from our previous section, if you have a diagonal, an upper diagonal matrix, you can multiply the pivots to get the determinant. So this says go ahead and reduce. Use row operations and reduce till you get an upper diagonal. All those row operations don't change the determinant unless you happen to swap two rows. So U here is your upper triangular matrix, and R is the number of row swaps. So if you swap two rows, multiply by -1. If you swap another two rows, multiply by -1 again. If you swap another two rows, multiply by -1 again. So however many times you swap rows, that's how many times you change the sign. And so yeah, let's get a little picture. This is from the book too. So if you do your row operations and you reduce your square matrix and you get pivots in all four positions, so you've got this upper, this U, then we know that the determinant is product down the diagonal. And if we just did A, if we just added multiples of rows to other rows, we didn't change the determinant at all. If we did some B, if we swapped rows, then maybe we swapped the sign. So we have to keep track of how many row swaps we did. We don't have to keep track of what multiple of one row added to another row we did. So yeah, if you reduce your square matrix, you get a pivot in every column. That's great. That means a lot of things, right? Remember the invertible matrix theorem? It means the columns are linearly independent, and it means we could ultimately row reduce to the identity, and it means a bunch of other things. It means the inverse exists. And that's important for what they're saying right here. So this works when the matrix is invertible. If the matrix is not invertible, that means you don't have a pivot in every column. That means that, well, no, still it's the product of the diagonal entries, but there's a 0 in there. So the determinant will be 0. And the matrix is not invertible. Then that means we didn't have a pivot in every position. Columns aren't linearly independent. Determinant is 0, and the matrix is not invertible. And we're actually getting one more line that we can add to the invertible matrix theorem. So we are getting this connection between invertibility and the determinant. So a square matrix is invertible if and only if the determinant's not 0. That makes sense for the inverse formula for 2 by 2's, by the way. Back when we knew it was 1 over AD minus BC. That's 1 over the determinant right there for a 2 by 2. And that's part of the formula for the inverse. But yeah, if the determinant is 0, then this inverse will not exist. But this is the more general picture over here. It says the determinant in this row echelon form comes from the product of the diagonals. If the diagonal has some zeros in it, matrix is not invertible, not linearly independent columns, determinant is 0. So yeah, out of all of the invertible matrix theorem, all of our A through L, they don't actually do it in this section, but we are essentially adding an M onto this and saying if it's an invertible matrix, determinant of A not equal to 0. Okay, so in the next video we are going to take a look at how to use this new language and these new ideas for some of our homework problems.